Hi everyone. In this video, I'd like us to have a look at the memo in a little bit more detail, especially if you weren't able to get the answers. This is a place that you should be in order to get a clearer image of what you should have done. So we're going to start off with exercise 1 of 3, which corresponds to exercise 2 from your textbook. In this question, you have x and y, and they're defined according to the question. So now let's look at the question since you already read all of that. So this is now a more detailed solution, and I'm going to go through it section by section so you can just see where the working is coming from. So in the first part, they've given you different probabilities. So this notation, note well, where they have x, lowercase x, and even for the y case, it's just short for saying the probability that x is equal to x. And this is something very familiar to you. It should be from chapter 3, where you dealt with discrete random variables and you said x is equal to a particular value. So what they're saying now in this question here is they want you to find the probability mass function, particularly the joint one, that's px of y. So in terms of the shorthand notation here, that's just the same as saying probably that x is equal to x and xy is equal to y. So now you're looking at them combined. So it's basically an intersection, in other words. So now when it comes to this question, they're saying that now you need to find the probabilities. They've given you these ones, these marginal probabilities. So that's the probability of a single variable on its own. And then they want you to find the joint probabilities. And remember, when you have independence, which is important, in the question, whenever you see independence, your mind should think back to the definition of independence, and it is given here on page 239. The joint probability of x and y is equal to now the individual probabilities whenever you have independence. And this is true for every single pair. So that means now to find all the probabilities, then we need to just multiply the probabilities that they gave us, and then we'll get the joint ones. So inside this table, in that rectangle, those are your joint values. And then here, in this result, those are your marginals for x, and then in this row, that is your marginal for y, okay? And now this is what they've given you in the question. Remember, they said the probability that x is equal to 0 is 0.5, so that's where this 0.5 comes from. X equal to 1, then that's where the 0.3 comes from, okay? So the easiest way is to just write it in a table like this first, and then now you can do all the products. So now, if you want the probability, for example, of x equal to 0 and y equal to 0, then you need to take the probability of x0 times the probability of y0. And then in this case, if you look at the question, they gave you 0.5 and 0.3, the product of those two things. Oh, sorry, I was looking at the wrong one. I mean y equal to 0. There, those two. Then 0.6 times 0.5 gives you 0.3, which is corresponding to that value. So the easiest way to do it is now with the table, like I said, having written py and xy, then all you need to do is multiply all the values across and down. So for that value, you multiply the 0.6 times the 0.5, and you're going to do that for every single value. So let's say for this value here, that's y equal to 2, x equal to 1. Then you need the probability of x equal to 1, which corresponds with that value. You need to multiply the probability that y is equal to 2, which corresponds with that 0.05. And when you multiply 0.3 times 0.05, that's how you get the 0.015. So you're going to do that for the entire table, and then you can always check yourself at the end. You need to make sure that all of these values sum to 1. So that's one way to double check if you would like to make sure that you didn't make a mistake. And then another thing, remember, marginal distributions are actually valid probability mass functions as well in this case. So that means even these probabilities here must also sum to 1. Okay, same thing also for the values of y. They all sum to 1. So in this question, technically, they only needed to give you at least 4 of them, and then you would have been able to find the other one if they hadn't given you every single one. So similarly, even for x, if they'd only given you these two, then you know that all the probabilities for x must sum to 1. Therefore, you'll have 0.2 once you've taken 1 minus 0.8 in this instance. And then for part B, they're saying now compute the probability that x is less than or equal to 1 and y is less than or equal to 1. So x and y, so at the same time, x and y must satisfy this condition that they're both less than or equal to 1. So the easiest way to do it is to just cancel out things in the table. So look for the region where you have x less than or equal to 1. So if we look here, 0 is less than or equal to 1, and 1 is less than or equal to 1, but not 2. So I would draw a cutoff there, so we don't want anything this side here. And then for y less than or equal to 1, 0 and 1 are okay, but 2, 3, and 4 won't cut it, so we're gonna cut them out as well. So then we end up with something like this. So now we only need to sum those 4 probabilities inside, which correspond with probability of 0, 0, 0, 1, 1, 0, and 1, 2. So you see every combination of x and y in the brackets satisfy the condition that both of them are less than 1 or equal to. When you sum now these 4 probabilities inside, that's how you get 0.56. Okay. Now they're saying here they want you to verify that now if you take the probability that x is less than or equal to 1 and y less than or equal to 1, that you actually come to the same answer. And this is stemming from that whole independence property. So what you're going to do now, similarly here, so remember you have your marginals at the bottom and the marginals are here and here. So if we want x less than or equal to 1, so remember this corresponds with the probability that x is equal to 0. This is the probability that x is equal to 1. So it's just the sum of these values, remember? Okay, and then if you sum those two values, you'll get 0, 8, which is that value there. And then you'll do the same thing. So remember, this value is the probability that y is equal to 0, and that value is the probability that y is equal to 1, which gives you 0.7 there, which comes to the same answer when you multiply them to 0.56. And then in C, now they're saying that, okay, we want all combinations of x and y where their sum is equal to 0. And obviously the only way you can do it, if you're looking at values 0, 1, 2, and 0, 1, 2, 3, 4, 5, the only way that you can sum x and y such that you will get the value of 0 is by taking x equal to 0 and y is equal to 0. So this is the only possibility. If you try to sum any of the other values, or 1 plus 1 will give you 2, and so on, then it's not going to satisfy what they want in here. So they say this is the probability of no violations. So this one is a direct question where you just read straight from your table because there's only one possibility. And then in part D, here you want the sum of x and y to be less than or equal to 1. So what you can do here is go through your table and then just see which value. So remember, here corresponds with 0, 0 from here. This next space there corresponds to 0, 1, x equals 0, y equal to 1. So then you can now check. So for this one, if you take 0 plus 0, that's going to be satisfying that condition. 0 plus 1 satisfies that condition, so you'll take that one. And then 0 plus 2, doesn't. So the moment you start going beyond here, your conditions are not satisfied. So you can go to the next row, 1 plus 0 satisfies it, and then 1 plus 1 doesn't work. So you're going to find for yourself, you can check the rest of them don't satisfy the requirement. So all you have to do now is therefore sum those three values that I ticked, and then that's going to give you 0.53. So that brings us then to the end of question 2. I hope everything is clear now if you weren't able to get all the right answers initially. Let's now have a look at the second exercise of the three. I trust you've already been through the question so you know what's expected of you. Before we carry on, the first thing though I want to just highlight is this table, it doesn't sum to 1. So in other words, when you take all the values and you sum across them, all the x and y values, remember for a valid probability mass function, in this case a joint probability mass function, these values should sum to 1. But in this case, they do not sum to 1, and the reason for that is because this is actually a snippet of the table from question 18. I cut the table because I wanted it to be a little bit less manual calculation for you. So the method is going to remain the same, but you just have to do it on fewer values because it's a bit repetitive. So just ignore the fact that they don't sum to 1 and just do the calculations following the correct procedure, and then that is what will give you the answers that I have here and even the answer that you will get for B. I am going to do exercises A and C in detail with you now. And for B, I'm just going to give you a hint because I want you to do it on your own and submit it as part of this week's quiz. Okay, so let's start off with the hint before we go on to part A. So have a look at this second block. Let me call it block 1 and block 2. Block 1 is familiar to you. Here I have the formula for the absolute value. So remember, the absolute value takes whatever you give it and then it gives you the positive value. So for example, the absolute value of 7 is 7. And then if it's already positive, the absolute value of, let's say, 1 is equal to 1. So mathematically, it is represented by this formula. So if I give you a value of x that is less than 0, so for example, in this case, I gave you minus 7, then you will give me minus of that thing. So obviously, minus 7 will give me positive 7. And then in the event that I give you something greater than or equal to 0, like I did here, then you'll just take it as is. So you'll just get 1. So now in the previous part in B now, in B you're asked to now find the expected value of the maximum of the two values. So in the simplest of terms, the maximum function works as follows. So you're going to give it two values. In this case it's 2, but you could actually have a longer list, like if you're doing it in Excel. But here, if you have two values, let's say the value of 3 and 7. What the maximum function does is it outputs the maximum of the two values. So in this case, it's going to be 7, all right? If you take the maximum of, let's say, 9, 4. So I put them now in a different order here. It'll give you 9 because that's the bigger value. So in terms of what the function looks like, I'm calling it f of xy because it takes in two values, and it always gives you the maximum. So mathematically, this is what it looks like. So if you have a case where x, the first value here, is less than the 1, the second one, then you're going to give me y. So here we have x and y, and you can see that here x is bigger. So it's actually an example of this case here. The other one on top is an example of the case on top. So the one on top, you have x is 3 and then y is 7. So x is less than y, therefore you give me y, which is your 7. The other one here, x is bigger than y, therefore you give me x. Okay, so that is just to explain the notation there, and then you're going to use this same formula here, but in place of your h of x, you take the maximum of the two values that you get. So hopefully that works out. Let's now have a look at part A, and then I'm looking at part C after that. So in part A, you are asked to find the expected value of xy, and you're going to make use of this formula here. So according to this formula, if you have some expected value of a function that's a function of x and y, then you just replace the x and y in there, and then you multiply by the joint probability of x and y, and then you need to make sure you go through all the possible combinations of x and y. So that's the easiest way to understand this formula. So what you need to do now, so in place of hxy, our hxy is xy. So this is basically what they have in there. And then according to the definition, you're going to put xy because that's your function. Okay, so now this, what does this mean? I said you're going to go through every single pair of x and y values. So when I say every pair, you can look at all the positions here. So in this position, x is equal to 0, y is equal to 0. So that's already a pair right there. Look at this position. It gives you x is 0, y is 5, this one 0, 10. So once you go through all of them, you will end up with all the possible x and y combinations that you can possibly get. So there are going to be 6 of them. 5, 10 is the last one. So I've covered every single position in that table. And then we're going to make sure now that we take each one of those pairs and we're actually going to substitute them in here, each one at a time. So first we take 0, 0. So in other words, here 0, 0 times p of 0, 0. You get that? The next one is 0, 5. So you'll take 0 times 5. So that's my xy times p of 0 times 5. And you're going to continue until you get to the last one, which is this one. So I went across the row, the top row, and then across the bottom row to get this. And then you just now substitute your x and y values. So now where you have p 0, 0, okay, you now need to get the probability from your table. So remember all the probabilities inside the table in there. These are all pxy values. So if you want 0, 0, then you need to go to where x is equal to 0 and y is equal to 0. So that'll give you your 0.02, okay? And then from there, you need to do it now for every single pair. So for P05, you'll see you get the 0.06, and you can carry on as well. For 55, you have the 0.15, and then for 510, you get the 0.2. So you need to make sure you have 6 of these terms that you're summing. So that's 1, 2, there's 2 represented in there, and then the last 2 I have already there. Now, when you work this whole thing out, that's how you end up with the final answer of 13.75. One other thing that I also want to just point out for you as well, which you might notice, is sometimes when you are doing these products, some values vanish. So you don't have to waste your time including them because they automatically become 0 because you're multiplying by 0. So for instance, in this case where it's xy, each term is multiplied by xy, then that means all of these terms here that have zeros, they're going to be 0 because x is equal to 0 for that whole row. And then even here where y is equal to 0 for that whole column. So you're actually going to lose a lot of the terms. So the final answer actually is only that 5 times 5, P55, which is 0.15, plus the last one there, 5 times 10 times 0.2. So you can save yourself a lot of calculations if you can be a little bit smart about it and you notice that, oh, okay, some of these terms become 0. And then for part B, this is just an application of that absolute value that we were looking at. So once again, you go through every single pair. So 0, 0, 0, 5, and so on. And then you'll substitute in here, okay? In this case, our hxy function is the absolute value of x minus y, which is in there. So what you'll do now, we start off with 0, 0. So 0 minus 0 will give you 0. And then 0 minus 5 will give you minus 5. Okay? And then you'll have to do it for all of them. So these are your different xy pairs, right? All of them. Okay, times p xy. All right, so once you've done all the pairs, so I'm looking at these same 6 pairs because it's the same table, and you'll end up with 6 of these kinds of terms. And then you need to remember to take the absolute value of the differences. So this minus 5 is what becomes positive 5 in there. And then here you end up with a minus 5 again, which becomes positive 5. And when you now calculate this, this is how you'll get the answer of 1.7. And then as a last note on this question, I think if you have access to a computer, the easiest way to do it is with a computer. So then what you do is you sort of enter, basically you're going to enter all your x values and the corresponding y values. So you got all the pairs. So the 0, 0 pair is that one there. And then the 5, 0, x of 5, that one, 0, 5, x 0, yeah. So I copied all of them in all the xy pairs, right? And then I end up with 6 rows naturally because I have 6 pairs of values. And then I took the probabilities that correspond. So these are now given in this column here. And then now if I want to calculate that expected value, then in Excel, I'm just going to say equals, and then I'm going to take this value here, okay, whatever it is. Let's say this is A column 1, 2, 3. I think it'll be easiest that way. So you'll select A1, and then you'll multiply by this value, which is A2, and then you'll multiply with this value, which is your A3. So, but that's only one of them. There's 6 of them. So you'll need to do it. Once you've done for this value, remember in Excel, there's a little square at the corner here. So if you drag it down, then it's going to do all 6 of them. And then when you get to the bottom, you can use the sum function. So you say sum, and then it's going to sum from A1 to A, I guess B, C, D, E, F, 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 yeah, A, sorry, it's gonna, oh, this is my 4th column, so it'll be something like A4 to F4. All right, so if you sum everything, all of these values, right, then that's what's going to give you this final value of 13.75. Yeah, so now you can do a similar thing even for the other columns. You calculate here. There is a max function in Excel, so you say equal to max, and then you have the product. And then for the other one, there is an absolute value. I think it's equal to abs, and then you'll put in your values that you want to take the difference of, and so on. You'll drag down and you'll sum, and then this will give you your final answer. Okay. So just a note, I think I did swap these round. In Excel, it's actually going to be the letters in the columns, and then the rows are actually numbers. But that is how you do it in Excel. This brings us to exercise 3 of 3. You have been asked to calculate the covariance of x and y and rho. Okay, so let's have a look. So these are actually the answers, how they got to the answers. So you can have a look there and see if anything there is unclear, because I am actually going to go through it in detail though if you're still not happy with any of those. So for the first part where they want you to calculate the covariance, you need to know the covariance formula. So the covariance is simply the expected value of xy minus expected value of x times expected value of y. So in order to calculate the covariance between x and y, we need to calculate these different parts here. So let's start off then with the expected value of x, and then the expected value of xy. I expect that you should be able to do it, but we'll talk about it briefly as soon as we've done the expected value of x. So the expected value of x is basically as you know it from the definition. Remember it's at xpx, okay? So that's from chapter 3. And in order to calculate this, then you need the distribution of x. And remember, we have a special name for it. It's called the marginal distribution of x in this setting. So now you need to just get the distribution of x. And you can see that x takes on three values, 0, 5, and 10. And then what you need to do is now calculate all the probabilities. So one for the probability that x is equal to 0, the probability that x is equal to 5, and the probability that x is equal to 10. And then that is actually your marginal distribution of x. So in order to get the probability that x is equal to 0, you need to sum across the 0 row. So all of these values, that 0.02 plus 0.06 plus 0.02 will give you the probability that x is equal to 0. So another way of thinking about it is you're looking for the probability that x is equal to 0 regardless of the value of y. So that's why you sum across all the y values. All of these satisfy that x is equal to 0, but then we're not so interested in y. There's no restriction on what y can be, so we sum across all the y values. And you're going to do the same for all the other ones. Just sum them, and then this is how you'll now get your probabilities for x is equal to 0, 5, and 10. And you can even check that once you've summed all of these, they do sum to 1, because remember, it's actually a valid probability mass function. So you could write it out like this, where you have the values of x and then your px, which would be 0, 5, and 10, and then you'd have 0 0.2, 0 0.49, and 0 0.31. And now the way that you handle it is the same way as you did in chapter 3, and you're going to put it into this formula there. So we take the 0 times 0 0.2, that's going to be that term there, plus the 5 times the 0.49, and the 10 times the 0.31. When you put them now into your formula, that's how you get the 5.51. And then the expected value of y is done in a similar fashion, but in this case, you just sum down the columns, and whatever answer you get here, that's the probability that y is equal to 0. So you need to do that for all of them. For y is equal to 5, 10, and 15, and then you will just do the same calculation, but this time you'll do for y. Okay, so you're going to sum over all the y values, y, py. So it's the same formula, same process, just different values. So that's going to give you expected value of x, and you'll need to find your expected value of y. And then for the expected value of xy, we've already done an example like this. You're going to follow the same process where you'll take the summation here over all the x and y combinations, substitute x and y, and multiply it by the corresponding probability of x and y according to your table. So this should give you then your answer of 44.25. So that is going to now give you your expected value of xy. And then when you combine it for the covariance, let me write it here, the expected value of xy, that's your 44.25. The expected value of x is 5.55 times the expected value of y, which is 8.55. And when you do this calculation, it gives you then the final answer of minus 3.2. Okay, so now for the covariance, the correlation. So remember why correlation is important is that now it gives you, it's like a version of the covariance that is standardized in quotation marks in terms of, now remember, covariance is affected by units. So if you calculate the covariance on the same data in meters and in centimeters, you'll get a different value, but then you eliminate that once you use the correlation. So whether you use the same data, let's say in meters or kilometers or centimeters, you will still get the same value for the correlation. So that's why we prefer to interpret the correlation, because it's then a value that's always between -1 and 1. Okay, so we prefer that versus instead of the covariance, which can take on any value from -infinity to infinity, and it's affected by scale. So now when we look at the correlation here, let us calculate it here. All right, so in this case now, you need to know your definition. So this is a definition you should memorize. It's the covariance divided by the square root of the individual variances. And the way that you go about it is now calculate the different parts. So we already have the covariance part. We calculated that previously. So now we just need the variances. And the variances, you'll do it now the same way. So remember this table with your marginal distribution here. We're going to use the same one, okay? But this time you calculate the variance. So remember the definition of the variance is the expected value of x squared minus expected value of x all squared. So what I'm going to do is calculate the expected value of x squared first, and you're just going to use those marginal values. So remember I said these were your probabilities of x, and then your x values are 0, 5, and 10. So in this formula where you have your x squared, you will take the square of these values, these x values. So x squared is 0, 25, 100, and then you'll multiply them with the corresponding probability there. So for the first one, it's 0 squared times 0.2. So you could have saved yourself time by skipping that part. And then the next one is 5 squared times 0.49, so it's this pair here. And then the next one is 10 squared times 0.31, which is that pair. And when you sum it, you get 43.25. Okay, and then once you have done that, then you just need to substitute it in the formula here. So we said our expected value of x squared is 43.25. And then the expected value of x all squared, we already calculated it there, which is your 5.55 all squared, and that gives you 12.4475. Okay, and in the textbook though, in the memo that they provide, they did round it off to 2 decimals. So if you have a small difference in the decimals, this is where it's coming from. Now that we have the variance of x, then you can go ahead and do the variance of y. Once again, like I said, you need to just find the marginal distribution of y and then calculate your variance, and then you should get 19.15. Oh sorry, I also underlined the wrong value. I mean 12.45. That's where they round this value here. And then this one is 19.15, which might also be rounded. And then once you have those, then you put all those values into the formula in the corresponding places. So minus 3.20 from there, and then now you'll have your different variances in here, and then you'll take the square root of everything. Okay, so before we round up this video, I would just like to pose a question to do with interpretation. So you can take a moment to pause the video and write down your answer to the following question. If I'd asked you to interpret this correlation coefficient, what would you have written? Okay, hopefully you have taken a moment to write your answer down, and this is what I'm expecting. So remember, correlation measures the degree or the extent of the linear relationship. So remember, you now look at the value. The sign tells you whether it's negative or positive, and then the absolute value will tell you the strength of that relationship. And remember, if you think of it in terms of, let's say, a number line, if your values are between minus 0.5 and positive 0.5, then in this space here, that's where we say we have a weak linear relationship. And then when you go up to 0, 0.8 and here minus 0, 0.8, so if you're now in this region or that one, okay, those two, then we say you have a moderate linear relationship between x and y, and then you go up to minus 1 and positive 1. And now if you have values in those two regions there, then we say that we have a strong linear relationship. So the answer for this question, what I would be looking for is, I want you to comment now. You need to mention the strength, the direction, and you also need to explicitly say that you are measuring a linear relationship. So how you'd write it, you would say that x and y have a, and in this case, is it strong, weak, or moderate? Here it's 0.2, so it lies in this region. So you would say x and y have a moderate, and then you can see the sign here, so you'll say negative, and then don't just say relationship, because correlation doesn't just measure any old relationship. It measures the extent of a linear relationship. Okay, so just because, let's say, values, your data might have a correlation equal to 0, that doesn't mean there's no relationship. It just means there is no linear relationship. So if I were to mark this question, I'm always looking for these parts. So probably half a mark for moderate, half a mark for negative, and half a mark for mentioning that it is measuring a linear relationship. So make sure you have all those parts if ever you have to interpret this for somebody. Okay, so this brings us now to the end of our discussion. I hope this was helpful. If you have any other questions, please don't hesitate to get in touch via the discussion board, and I will gladly assist you. Enjoy the rest of your day. Bye.